Okay, everybody, welcome. We're at another podcast. Hopefully we're getting better. We got with me Bob Licari as usual. Today, I'm pretty excited. I got Ray, top man engineer Wertz here. I've known Ray since, you see the very royal. I've known Ray since, now how many people can you say the date you met somebody? And it was 29 years ago almost. August 12th, 1996, I met Ray Wertz. Ray Wertz is running the connector room.
Yep.
And I got assigned, you know what I did all day? I made ST connectors all day long.
Oof.
Ray was
Who'd
like
you piss off?
Ray was like a taskmaster behind me. He was like, and I remember you had a board with a light, and you would put the ferrule holders in, and then the light would come through, and you have to look in each one, make sure it wasn't clogged up. And then you put the spring on it, and then you attach the ST body. It compressed, and then you put this little C clip, or they also call them like Jesus clips or something, right? Where his hands are out with a little tool, and that was the hardest part. And I realized after that day, I don't really want to do this.
It's screwing up my whole production.
I bet.
They keep records on how many connectors like someone did in a day. Yeah, I got the lowest record, I'm pretty sure. And they knew right away I was not going to be in the connector room. So I appreciate you being here, Ray. Ray and I have known each other for almost 29 years. I will say something about Ray. I feel like he might be my father, because every time I say something or bust his chops or pick on him, he just has that dad, like, oh God, like always disgusted with me. I haven't turned out the way he wants me to be, and I'm trying to live up to the Ray standard, and it's not that easy. So Ray, welcome to Fiber to the Podcast. Hopefully we're getting better at this. The first couple. Tell everyone, the billions of people listening, literally. When did you start? What do you do? Give me your histories. Talk about. Come on.
All right, so I have been here at FIS since January of 1995, so I'm 29 and a half.
He's got me by a year and a half-ish.
Yeah.
Yeah.
I was, a year and a half when you joined in. Originally, born out in Spokane, Washington.
Oh my God, I never knew that.
Yeah.
You were born in Spokane. The family was in Spokane?
Well, we were an Air Force family, so I was born on Fairchild Air Force Base out in Spokane. My father was.
I never knew that.
Was father was part of Strategic Air Command.
SAC, yeah.
Yes.
No, it wasn't. So he must have went to Griffiths, because Griffiths was like the northernmost point in Strategic Air Command, correct? Griffiths Air Force in Rome.
Then here in the east.
Yeah.
In east of the United States.
Yeah.
But that was so. In my first 2 years, went from Fairchild Air Force Base in Washington to Westover Air Force Base in Amherst, Massachusetts, for like a year.
Do you remember that? Were you too young?
I was too young to remember.
Yeah.
And then his last posting was here at Griffiths. So
he spent the majority. You were the majority was here at Griffiths.
Right. So he retired like when I was 5. So we were only
here
for like 2 years at Griffiths when he retired. So he was sort of in a position where he'd already been in the Air Force for 25 years, so he's eligible. And they gave him a choice. You can either retire, you can retire, and we'll bump you up a grade to Lieutenant Colonel.
He was a lieutenant?
He was a major.
Major. I get him mixed. Sorry. It's pretty impressive.
But if you stay, you're going to get rotated out to Guam to fly over North Vietnam.
Did he fly?
He was a navigator on the B-52. Yeah.
Jeez, all these things I didn't know. Did he ever go combat missions at all?
No, but he was part of Chrome Dome and that whole basically orbiting just outside of Russia, waiting for
really.
Yeah.
I had.
The
think
Cold War days,
Yeah, and you think you know somebody. That is good. Now you're 4 of you. 2 brothers, you and a sister? No, I always screw it up. I know you got a sister.
Right. 1 sister, 3 brothers.
Yeah. Oh, okay. I was off 1 with the brothers. Wow, Washington. I had no idea. So, tell them your history. Where'd you work before FIS? Bob's not going to know this at all.
Before here, I worked at T-Hands, which is a local department store.
I know
Family,
T-Hands.
you don't remember T.
Yeah, I remember my parents used to go there and shop for furniture and stuff when I was a kid.
No kidding, because they had to close.
That was by
90s?
where Cafe Del Bono was.
Yeah. Where Party, no, Hobby Lobby is.
Hobby Lobby, yeah.
Yeah.
Right. Yeah. So I was there actually. I worked there pretty much straight out of college. I was there for like nine years.
And you sold my parents a couch. Oh.
No, I was
You were electronics.
Oh,
yeah. So Ray, we were talking, like 5 people came from T-Hands to here. You know Eric Vanderwater? He was T-Hands.
Really?
Yeah, he worked in electronics. So then you moved here in 95. First job was sales, right?
Yep. At the time, we had a sales force of 6 people.
Oof.
Wow.
Yeah, incredible.
Right.
No international department at that point, right?
Yes, there was an.
So Valerie had started international.
Right.
Oh, okay.
She was the international.
She was the only one, yeah.
Right.
Okay.
But there was technically 4 domestic salespeople, customer service.
Yeah.
So when, around what time did things really, take off?
Well, listen to this. Listen to this. Tell Bob, we were talking about this. What was your, so we have quotas, right? What do you think their weekly quota was for
Weekly?
sales? Yeah, what were they shooting for?
Back in '95.
$5,000
Yeah.
a week?
Ding, ding, ding. Yep.
A person.
Wow.
Yeah, they're $20,000 a week. If we did $20,000 in an hour, we'd be in trouble, right? I mean, the earth would be ending. And what was your biggest, you had a big sale or like
So my biggest sale was like the last week I worked in sales before I moved in.
he did so good, he got out of the job.
I did an order for, I think it was 108,000.
Wow. It'd be like $1 million order today.
Right.
Oh, yeah, easily. Like that was probably the biggest order they ever had.
It was close. Like
Yeah.
I said, they had done some larger orders back during the Gulf War.
Oh, yeah, it was pretty busy back then, the golf. So then you moved to,
So then we had just started producing our own connectors, the ST connector.
yeah,
And they really didn't have a manager of their own. It sort of was, the general manufacturing manager was sort of trying to handle patch cords and everything
yeah,
else. So,
it's just too much.
Right, so
Scott, right? Scott at the time?
yeah. So they put me back in that room because they needed to develop fixtures, and at the time, the little drills that we have. At the time, we were trying to drill our own
Stainless? Yeah.
127 micron
Yeah.
things, which obviously did not work.
Oh, we were like taking the blanks without holes and trying to, the concentricity's tough on that.
Right, yeah, you couldn't get anywhere.
So yeah, for those of you who don't know, concentricity on a connector is, tell me, because you're the engineer,
Right,
how dead center the hole is.
correct.
And, when you're using fibers, single mode 9 micron core is like 1/11 of a human hair. It's the mating, it's how well those two meet up. Bob, do you know, Ray probably knows this because connector room. Here's a good tech fact for everyone. What's the difference between a single mode and a multi-mode connector?
Without fiber in it?
Yeah, what's the difference? Why is a single mode connector more expensive than a multi-mode connector? Because, here's a couple things I've heard. Well, it's because it's single mode and it's more. No, we would never do that. We're not going to raise a price on something just because of what it is. So what's the major difference?
Is it the circumference of the dome?
No, well, I mean, there is that comes into play, but those, so, and correct me if I'm wrong. A lot of people, okay, when you teach too, you talk about, one of the questions I always ask is when we go through the 2 types of fiber, what's bigger, single mode or multi-mode? Everyone always goes, well, multi-mode. No, it's not. It's the same size. Technically, they're 125, right?
Yeah.
So then you ask the question, well, then why are single mode connectors more expensive if the holes are the same? Because people say, well, it's the size of the hole, right? No, it's concentricity. Am I right?
Right.
So I'm pretty sure when they make a ferrule, this is the numbers I got way back. When they make a ferrule, they're shooting for it to be single mode. That's their goal. And I believe the concentricity, how dead center that hole is like 1 micron or less. I'm pretty sure is the concentricity tolerance. Multi-mode has a less stringent concentricity value.
Lower tolerance.
I think that's like 5 or less.
Right.
So technically, what is a multi-mode ferrule? It's a failed single-mode ferrule, because you're going to pass more at 5 than you are at 1. And I was told at the time, I don't know if they're better at this, that only about 10% of the ferrules are good enough to be that 1 micron concentricity. So that's why they're more expensive, is they're harder to produce.
Harder to make.
Because of the concentricity. Now, so
Makes sense.
you technically, Ray, check me if I'm wrong, if you're doing connectors from the bottom up, from epoxy and polish, which in the field is ridiculous, you could use a single mode connector on multi-mode, but you would never want to use a multi-mode connector on single mode.
Right.
Yeah, because you're off by 4 or 5 microns. That's almost the whole core.
Right.
Yeah.
The core offset would be so massive.
Yeah.
Your loss would be.
And I can imagine trying to drill blanks. It'd just be impossible to get so perfect.
Right. So I mean, obviously for your stainless alloy ferrules,
Right.
those are strictly for multi-mode. You can never do a single
Well,
mode.
back reflections are such an issue with stainless, right?
But even drilling, at best, you're going to have, at best, 3 micron concentricity. Most of the time, it's going to be anywhere from 10 to 25 microns.
I know we put a plus or minus in when we do the drilled connectors, because the bigger multi-modes require stainless because there are no ceramics hole sizes. So you did the connector room for how long?
2 years, 2.5 years. Yeah.
I'm waiting for like the sales story. And then I had the biggest production day of my life, and they moved me away. Like you had the biggest order.
Yeah.
And then that was when engineering hit, right?
Right. So we had technically had an engineering department, but it was just one guy doing it.
Ragtag group of guys.
I'll be honest, to be honest about Ray, if we could duplicate that man like 10 times, we would be so much better off. I always feel bad because you're working on 20 things at once, right? We've tried to reduce that in the past, but it just never seems to happen.
Right.
So I'm sorry, I interrupted. So 97?
Yeah, 97 or so, summer of 97, was brought into, well, it was sort of dual role of tech support and engineering. At the time, for the most part, we were just doing sort of manufacturing engineering for the stuff that we were making.
Right. Yeah, so this leads me up to, and I mean, that's pretty much been your role ever since, right? So this brings me up to, and Bob's familiar, we've all sat in on the CPR meetings. We'll talk about CPR, why are we talking about engineering today? Because, I mean, your job is not just in-house engineering, it's to engineer products that the customers come to us and say, can you make this?
Right.
What do you think, out of 100% of the things, because you're the one who vets them and says, we just can't do this. What percentage do you think we take on out of 100%?
We try to take on all of them.
Yeah.
Basically, we take them on until we realize that we can't
Yeah,
take
it goes
them.
past our capabilities.
Right.
Yeah.
In general, I would say probably 60 to 70% we're able to pull out. You'll get some that are just way out of our league, and they don't even make it to committee because they're just things that we can't do. But
Yeah, because we only typically will see the stuff that's already been vetted,
Right.
And several hundred of them we've probably done.
we are at CPR like 490 now.
Oh, wow.
Yeah.
So name some of the requests that we've gotten to do, like to modify and to make new, right?
Right. So you have everything from custom assemblies, like very high fiber count custom assemblies, or with mixed connectors. Do a lot of in the past we would do a lot of MPO2, whatever, hybrids.
Yeah.
Since we've been making our own rack mount equipment.
Yeah, risking the arms.
Right.
Yeah.
So that's been probably the majority of things for the past 4 or 5 years, making custom racks.
Yeah, that's our sweet spot.
Right, custom
We
panels.
really, Risking the Arms is a sister company, part of Giotto Enterprises. They're called Risking the Arms. They built the 1911 handgun, but really, the vast majority of that building, which doubled in size 2 years ago, they're Armada machines, right? They punch stainless and reduce stainless and aluminum, right?
Right.
And we powder coat, we do all the wall and rack mount boxes, we do a lot of customer ones where we'll do it in their colors and their logos, and you're constantly getting, well, can you redesign a box to do this? Can you redesign this to do this, right?
Right.
And we recently made a fixture that you can see in our catalog that it goes into like a ceiling tile, right? And then you can put all the electronics and fiber in there, and it just fills in the ceiling tile.
Right.
Yeah, that was a great product.
A 2 foot by 2 foot standard ceiling tile. It just replaces it and goes up there and mounts.
I can think of a good project recently was the canister.
Yes.
The canisters.
Is that the robot one that deployed the fiber? Yeah, that was a really
Right,
great
that's
one.
probably
Pretty
one of the
successful.
coolest project. That
Yeah. You've worked on some cool stuff. We all get the cool stuff. We get the everyday mundane stuff too. But so I wanted to make sure that people, they have an engineering request, they can submit it, and it goes through committee, and you'll get ones that we can do in a month. We get ones that take a year and a half. So I got some questions. Talk about a day in the life here of Ray Wertz. What are your daily functions?
Okay. Well, my main job is to be basically supervisor of engineering. So
Right.
as you were mentioning, when projects come in, I'm the one who vets them and help prioritize them.
Yep.
And bring them to whatever assets we have here to work on them. And usually I'm the one that's the liaison between engineering and sales, or engineering and manufacturing, to get things done, or if issues come up, to help solve the issues.
Yeah, like an RMA or
Right.
Yeah. So, do you remember we invented? We didn't invent it. We tried making our own cleaver. Do you remember how long ago that was?
Oh yeah, the coffin cleaver.
The coffin. We called it the coffin cleaver. We could never. It was weird. It was on like an offset spin.
Okay, so there was two. You missed. Okay, so the original coffin cleaver was before your time.
Oh, the original. Oh, I didn't know there was an original. I thought I was here or when I was
No,
here.
the original coffin cleaver, we called it that because it looked like a little coffin.
Yeah.
And right, it did have. It was a spinning blade inside, but that
It wasn't circular. That's the second one.
Right.
It was like on an arm that did like a weird rotation.
That was Gen 2.
Okay.
Neither of them worked, but
You're talking 25 years ago.
yes, this was, yeah.
What was the conclusion was what? It's just so hard to get that perfection done.
Well, yeah, I mean, your blade, like I say, a fiber is, whatever we're saying, 1/11th of a human hair, and you're trying to get that blade to nick the first 3 microns. Go any deeper, you shatter it. Any less, you don't hit anything.
So it was a consistency thing, right? Because sometimes it would be perfect, sometimes it was just.
Right.
I remember we put a lot of effort into that clear. I don't even know if Bob even knew we tried to make a clear, Bob. It was the Japanese are very good
we
at
ever
precision.
sell any?
No,
No?
I don't think so.
No.
I don't think we ever released it.
Okay, it was in like 4 catalogs.
Because it was like
coming
because we got
soon.
this thing go. We got this thing.
It's coming.
Perfect.
It's coming.
Coming soon, but
Yeah.
never. Yeah.
So, what do you think the best thing you've worked on or invented or made here? Like, what was your biggest success?
Our splice on connector.
Yeah, I agree. 100%. Great product. Cheetah,
Armadillo.
Armadillo. So the Cheetahs for the 900 micron, the Armadillo. Excellent
Armadillos
product.
for 3 mil.
Through mill.
I think
Yeah.
the numbers were just huge last year.
Tens of thousands. Yeah.
Huh?
Tens of
Oh, I
thousands.
think at one point I saw, what did I see, like 8,000 a week were going out or something
Right.
ridiculous when we were, yeah, I agree, that's probably the best thing. We've made a couple things that just weren't, we thought we had it, tiger by the tail, and it wasn't popular.
What was your most difficult project that actually that came to fruition?
Trying to get the scope to work.
The microscope,
yeah.
the benchtop scope?
Right.
Yeah.
Yeah.
Get that to work properly
Yeah,
all the
'cause
time.
Correct me if I'm wrong, it's like you get one thing figured out and then something else comes
Something,
up.
yeah.
Right. It's,
But it'll be finished eventually, right?
yeah. I mean, yeah. There's just so many moving factors that not all of it is development issues. There's been a lot of factors over the past few years that
Yeah.
made things difficult.
Resolutions, image, lighting, centering,
Right.
lenses,
getting
sourcing,
sourcing. That's been the big thing.
Yeah.
So.
So let's talk about some of the stuff that you've incorporated here. 3D printers. Why did we bought 2 or we have 3?
We have three different styles, or we have 3 different printers.
So talk
different
about
styles.
what we use them for in-house and how we can use them for the customer. Like samples and
Right.
talk about some of the stuff you've done and what we do.
Okay. So originally the reason why we got this technology was so that we could turn around samples, particularly of plastic parts that would mean we'd have to spend $5 or $6 grand on a small mold just to see if
it was feasible.
Right.
Yeah. Right.
So we started off with a simple tabletop extruder style 3D printer, something that you'll see. You can go down to Kmart or whatever and buy these.
But then we stepped it up, right?
Right. So we then went into what's called an SLA style.
What's SLA?
Stereolithography.
That's the material?
Well, that's the process.
Oh, okay.
So most 3D printers that people see, and the ones that you can like buy in, out in the stores, use a plastic filament, and there's a head that basically melts the plastic, and it's sort of like a dot matrix printer, and it just sort of builds up the layers. They're decent. Their limitation is the resolution just isn't the resolution that we need here, especially.
So the specs, the measurements,
right.
You just can't hold the tolerances.
Right. You can't do fine detail and your tolerances.
So the SLA.
SLA is designed. You can have features that are measured down in
thousands.
Right.
Really?
Plus or minus 2,000s, whatever tolerances. So.
How it doesn't melt the plastic? How does it?
No. So SLA.
Use like a resin or something.
Right. So there's a tank of resin that sort of looks like ink or paint. The tank has a clear plastic bottom. There's a laser unit that's underneath it. You have a build platform that sinks itself down into the resin, and it will bring itself down to whatever the layer thickness of whatever you're printing. So 50 thousandths, 25 thousandths, whatever. The program will take whatever you're trying to print, slice it up into 100 or a couple of thousand layers. And what the laser will do is trace out a layer, one layer at a time, shining up through the resin, and when it hits it, it instantaneously hardens it.
Really? But when the laser hits it?
Right.
Really?
Right. So it will go through, it will trace out one layer. The printer itself will then, since it's both hardening to whatever you've already printed, but it's also hardening to the bottom of the tray, it sort of has to peel everything off the tray. The tray is made out of extremely non-stick material. The head will recenter itself, put another layer of resin, and then it will do the next layer. So what it looks like, if you sped it up, it looks like you'll see a platform rising out of the goo with the part dangling underneath it.
Yeah, I got it.
But you can do extreme.
What do we use it for?
Well, this is the holders for our SOC connectors. We now make through this method. We used to have these either metal molded.
We used to just plane them out or whatever at this machine shop.
Right.
The difference between the metal one and this one is just consistency, or
right. The machining, we were having problems with the consistency of the machining.
Just replicating the process over and over.
Right. And we were sort of stuck with making modifications to it. There's only so much you can do with a molded part because it's not solid. There has to be voids and stuff so that the wall thicknesses would be the right size. So one of the things that we can do that our competition really can't do with their SoC connectors, if you have a splicer that is capable of taking the
Removable holders.
Right.
Yeah, the
removable
clamps.
holders,
Yeah.
we can make a custom.
Yeah, I know we've used you guys. I've used them for a couple because you get these oddball machines, and they want to use our SOCs, and you guys have made
Right.
them.
So with,
That would be impossible, probably, or a lot harder doing it the machine shop way.
right, it's almost impossible to do it in the machine shop. But with this, since all I need is computer with SolidWorks on it, you send me the splicer, I take a few key measurements, and I can design up the holder in SolidWorks,
Right.
port it over to the 3D printer. 3 or 4 hours later, I have a sample to test, and even if I have to make a little
Tweak. Yeah, you can try it out.
2
tweak
hours
it.
later, I have, and you just can't do that, machining. It would
Yeah.
take a couple of weeks.
Do we use it for other things?
We use it for some internal components on various items.
Okay. So how could we use it for a customer? If they needed a sample of something, if they designed, have you used it for samples for other things?
Usually,
We made a sample of the canisters with it, didn't we?
right, so,
Oh, there you go.
We
Right.
3D printed them.
Right, but that was not feasible to do that every time. That
No.
was just, and then we moved it to our plastics company, right? MSI.
Right, well, it's-
We got it molded, yeah.
Yeah. Now we have a mold, but the original design came off of the 3D.
right, so the original design and what they use for testing the concept.
Yeah.
We use this.
I know those things are running almost every time I go by.
Yeah.
They're used a lot. They got to be a lot more expensive than your typical off-the-shelf ones, right?
Yeah, you're going from $400 or $500 unit to a $10,000 unit.
Phew, really? How much does the tank? Like, how long will that last you? One tank?
Depends on what we're printing, but we go through a lot of them. We're the Forum Labs, the company that makes our SLA machines. They love us because we're one of their best customers.
Because we're constantly using it. Yeah,
it's
yeah.
a printer. They make their money off the ink.
Yeah.
Yeah, exactly. Like Emerson, they don't make money on the printer itself. It's all those cartridges that you buy.
Right.
I know that there was a problem with, what do they call them, ghost guns or something? Where they, I guess on the internet, they put a
You can make a gun without any metal in it. by
plastic
3D
gun.
printing it,
Yeah. Isn't that insane?
Yeah.
Right.
The technology's amazing. So we're going to talk about some specs too. Now, you had said, why don't we talk about Telcordia, I always screwed up, GR326, is that right?
Correct. Yeah.
All right, so how does that play a role in our lives here?
Okay, so GR326 is a standard for single mode, basically for single mode patch cards. Yes, GR326 is for single modes, and I think it's EIA,
Yeah, ATIA?
right, TIA
5-something.
528 or something like that
I'm terrible with those numbers.
for
Terrible.
the multi-mode. So basically, yeah, so it's a standards package that will describe everything from what the operation criteria are supposed to be for the connectors, such as insertion loss.
Yep. Does it also define ORL for
Right.
UPCs and APCs?
Right, that's where you get those standards from. It tells us what the geometry of the end face of the ferrule should be when you polish.
Right.
It's also for testing, environmentally testing the connectors, for.
Oh, that includes environmental testing too. Does it include like pull tests, like how strong it has to
Right,
be?
then those are the mechanical tests. You got your pull, your twist, your impact test.
Is that the same for different connectors? So another LC and ST, let's say, would they be the same numbers?
For the most part, they do make slight revisions or deviations for the small form factor. So when the LCs and the MUs came out, they changed some of the tolerances for those because they're a lighter connector. But in general, you're testing the same thing.
So we have the ability to pull test, we do the twist test.
Right, so we can do all the environmental tests because we can do it in a chamber. So all your heat cycle, heat age, heat cycling, humidity age tests.
Oh, we can do humidity in that chamber?
Yep.
Oh, I didn't know that.
Yep. Then we can do the various tensile tests, straight pull, 45 and 90 degree pulls, twist tests, vibration tests.
It reminds me, it's almost like an airplane when they test one, where they'll pull the wings like almost straight up. So they put the spec higher than what you would ever usually see in the field, like
Basically.
Yeah, is that how it is with the connector? It's just a kind of an extreme.
Yes, I mean, yeah, like the temperature specs go from minus 40 to plus 85 Celsius, which,
Oh yeah.
I mean,
Very cold and hot.
Yeah.
right,
Yeah.
I mean, you could find yourself at, the South Pole and get colder than that. or
Yeah, exactly.
Out in the middle of, the Sahara Desert and get hotter than 85,
Yeah.
but you're going to cover 95% of all applications
Right.
in there.
Now, Bob, and I'll ask Bob and
Yeah.
Ray, what's the movement on the new connectors? A lot of people don't, when I talk about this in class, there's a couple that stand out, like, was the MDX from... MDC from
US Connect.
US Connect. And then Senko has that SN, I think it is.
SN, yeah.
And I know, like, the MDC, for those of you listening that don't know, you can put 6 total fibers, so they're duplex. So it'll be 3 connectors in the same footprint as an LC. And I know I think it's the SN. You can do, there's another one, SN, and I can't remember. It's one of the two. You can do 4 total duplex connectors in an MPO footprint.
So they're essentially high density connectors.
Oh, but it's... The pictures I have in the manuals of these, and they're just more for
data center.
FYI, though,
Yeah.
like, this is something you might see. When you look at like, the pictures in the manual are actually too big. Like, it makes them look bigger than they are.
Right.
Have you worked with either of these?
The MDC, we've been working.
You look at a panel, and it's got, instead of 24, it's got like 72 or whatever the times 3, right? Maybe 72, I think. What's your thought on these new connectors? You think they're going to be universal? Like, because I remember when the LC came out around 2000, there wasn't much use there. But
It takes 2 to 5 years for a connector to get adopted.
Right.
And yeah, the connector, it needs to find somebody big like a Google or a Verizon to adopt it.
Yeah, so I had heard, and I don't know which way's which, I heard Facebook took one, and then I heard Google took another. Like, they use 2 different of the 2 I mentioned. I mean, yeah, it's a large scale. I talked to a guy who was working with 6,912 fibers in one cable. So can you imagine the port size, even at LCs? So they were using these new ones, but really not much play yet, right?
We haven't seen it much yet, but we've been getting inquiries.
Yeah.
But like I said, connectors have only really been out on the market now for a year and a half.
Oh, the new ones, yeah.
Right. And like I said, it typically takes 2 to 5 years for...
Do you think there's a clear better one, or do you think there's a winner? Because a lot of times it's how you market. Sometimes it doesn't even have to be the best one that takes over.
Right. It like I said, it depends on whoever can get, like say, your Googles, your Microsofts, whoever's doing the biggest data center builds at the time. If
And then
you get into that.
Yeah, then I want what they want, and
Right.
yeah, it's just such a huge scale. It's mind-boggling. And then, can you imagine getting your fingers into like number 7,222 out of 10,000? I mean, the density is so small, and it's. Do you see any other new ones besides this? Maybe there's ones I don't even know of.
So far, no. These are, like I said, these are still trying to.
Because you wonder who's working on maybe the next big thing. I remember
Wasn't
Go
US
ahead.
Connect working on like a mini MPO?
Oh, that I'm not familiar with.
When I went and visited them in Hickory a year or 2 ago,
Yeah.
they mentioned it to me, but it was still a ways out.
Yeah.
I can't
Mini.
remember. I think it had the same amount of fibers, but the end face
Was smaller?
The footprint was smaller. Yeah.
Okay.
I know they keep adding more fibers into their current MPO.
Yeah, I mean, we got 16s, 32s. I had a
They-
person
they have
request a 72.
Right.
Yeah, 72 fibers. Get one out of order. Mind-boggling the amount of detail you have to do when someone's got to physically put those fibers in there, like us. Don't mess one up, right?
Right. So probably one of our biggest back in the early days, manufacturing goofs that we did here. A company had sent us a bundle. I think it was like 512 fiber bundle.
Oh, really?
In which we were supposed to cut off. I think they had ST connectors, and we were supposed to put. I think we're supposed to put LCs because LCs was the new
hot thing. Yeah.
And on the other side, they went into. It wasn't really a connector. It was a bundle that was sort of encased in like an epoxy.
Yeah.
And
Just bare fibers?
Right, but angled and polished.
Yeah. The bundle was angled and polished? Really?
Right. So we accidentally cut that off.
The part that was bundled?
Right.
Oh,
and
God.
apparently that was like an $8,000
Mistake? Yeah.
Right.
That's how much it costs to have it done.
Right. But these new connectors are going to become like that. It's basically you're just packing fibers literally on top of each other in a bundle.
Yeah. I remember when I first started, the big thing they said they were working on like speaker plugs, when you push the tab down, slide it in, and let go, and it's just held in by pressure.
Right.
Oh, the big thing was you're gonna just cleave your fiber flat, push down a button, slide it. Well, haven't seen that, have we? You heard all these different things. We're working on pushing power through fiber. I got a little game I wanted to play, Ray and Bob.
Okay.
Maybe Jeff can keep track of the scores here. Let me take your pencil here.
Yeah.
All right. Let's see here. You know what we're gonna do? Here's what we're gonna do. Turn your paper. Take your pen.
Yeah.
Open that drawer. There's a pen in there. I'm gonna have you write your answers down.
Yeah.
That way you don't buzz in or anything. All right, you ready?
Yeah.
So you got our pen, right, Ray? All right, ready? Don't let each other see this. So we use a lot of Kevlar and fiber, right? We know the real name is Aramid Fibers or Aramid Yarns, right? DuPont makes Kevlar. That's why they call it whatever. All right. We know it's really strong. How much stronger is Kevlar than steel? How many times stronger is Kevlar than steel? And the one who gets the point is the one who's closest. What Ray's got? Damn it. What do you got?
5x.
5 times.
10x.
It's 5 times.
5
How you knew that? You work with a lot of. All right, Ray's got a point. That was a tough one. These are tough, but there's a couple, Bob, that are in your wheelhouse. Does sound travel faster in air or in water?
Water.
That's your answer. Is that your answer? Supposed to write it down. Does sound travel faster in air or water? So we know Ray's answer is water.
I'm going to go water.
Okay, you both get a point. That's right. Now, why is that, Ray? Because I know light travels slower through water.
It's denser. It's a denser medium.
But you would think that would slow it down.
Well, you have more of a medium to go through.
Really?
I just went because
Ray said it.
Well, no.
No,
I learned that your voice carries better over water.
See, I didn't know that either. That's right.
Yeah.
That's
Sound
right.
goes a lot further in water.
I didn't know that. That blows my mind. All right. I guess that's why, too, when they do the whale calls, these whales were 5 miles away and we could hear them.
Well, back in the day, you remember when Gould used to be the big coupler company?
Oh, God, yeah. Gould coupler.
So,
Yeah.
I mean, they made their money. The underwater sensor nets that NATO used to use to track Russian submarines.
Really?
Use those.
Really?
And
No clue. Does Gould still exist?
I know they moved to India.
We used to sell a lot of Gould couplers and splitters.
And you think if water's denser, maybe that's why there's less attenuation or dispersion of the sound waves.
But see, in my brain, it would be
when it's in air,
slower.
it kind of spreads out more maybe and disperses quicker.
Now, this one you have to be precise on or you're not get the point. You ready?
All right.
LASER is an acronym of what? Ray's dropping his head. We might have a... See, now Bob does this in class, so I'm pretty sure he's got... But you got to get it perfect, because sometimes a couple of the letters people have a little bit wrong. LASER... I want to sound like it. Ready? The password is LASER. No?
I know the first two, but I don't know the...
All right.
Okay, I think I got it.
Okay, let's-
I probably don't.
Let's do Ray because he's questioning. I don't want him to steal
Okay.
your thunder.
Yeah.
Yeah, I know the light amplification, and that's where it ends.
All right.
Light amplification or light amplified
Light amplification.
radiation, source emitting radiation.
No points given.
Damn it.
Light amplification by the stimulated emission of
Oh.
radiation.
Oh.
I thought for sure. LED's easy, right? Light emitting diode, right?
VCSEL's easy.
VCSEL's what?
Vertical cavity surface emitting laser.
And we use them in what type of fiber?
Multimode.
And they replaced what?
LEDs.
Right, because LEDs can't do gig. See?
LEDs can only do 620
Oh,
meg.
620 meg, yeah. I always say in class, we didn't give up on laser or LEDs. They gave up on us, right? So, okay, see, this one's unfair for Ray. At what temperature is Celsius and Fahrenheit equal?
That's easy.
You guys know that? I mean, I know Ray would. You know that, Bob?
Oh,
What is
yeah,
it?
minus 40.
Yeah. All right. It's 3-2, Ray over Bob. See, I'm stupid. I like dumb stuff like this. Now, this one's unfair for Bob. What is the 7th color in the fiber color code? This is good.
I know the first four and I know the last four.
Well, that's the process of elimination, is so you can at least get rid of 8. Now you got.
Okay, I think.
Yeah, put it down. Don't say it out loud. Look at Ray. I don't know if I've seen Ray concentrate this hard in my life.
The 7th?
7th. It's sick that I have this memorized because something in my brain has gone away because I know this, right? Now, you know there's actually 16 colors too now.
Yeah.
They added like magenta, tan, lime green, and I can't think of the other one. All right, we'll go to Ray.
I guess yeller.
No, so it's blue, orange, green, brown, slate, white, red, black, yellow. So yellow's 9. What did you say?
I said yellow, but I was trying to. You just gave the answer away.
Red.
Yeah.
Yeah, well, but you're an honest man. It's
Yeah.
red. Blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, aqua. Now, if you ask me to say it slow, I have trouble. I have to fly
Say
through
it
it. I'll be
fast.
like, blue, wait a minute. All right. Okay, you ready? What is the industry standard, percentage-wise, for conduit fill ratio? So in other words, when is 100% of a conduit considered full and you're not supposed to add more to it?
It's a percentage number.
You know it because of class. See, that's an unfair Bob. All right, we'll do Ray first.
I'm going to say 60%.
60, what do you say?
40.
It's 40%. Now, look back at the conduits you might have seen in the industry or you've seen in the
Not
field.
many people follow it.
40's like, that's just starting,
Yeah.
right? I've seen some New York City conduits that are like 107% full. I don't know how they do it. They got like a stretcher. Like you couldn't literally sneeze and have the air go through it. But it's 40%. I mean, that's a true number. Don't look here, Bob.
I can't read
Bob
writing
gets-
anyway.
So we got a tie score. This is what I like. I don't want to run away. All right. What's the first U.S. city to use fiber optics for telephone transmit? And so this is a 3-point question. What was the first city? What was the year? And what was the speed it transmitted at? Oh, that's right. And I always love watching like game shows because the guy that's hosting it always looks like the smartest man in the world, but he's got the answers, right? So I know this. I will say Trebek was a pretty smart man. So it's what city in the United States? I'll even give you a hint. It's not like one of them. It's not a massive city. What year and
Is
what
it
was
a
the
US
speed?
city?
This is the first U.S. city. Yeah. Well, that's a big sigh.
The year is gonna be tough.
I'll give you another. I'll give 4 points. Do the state and then the city. You'll get a point for state and city.
New York, Corning, 1977.
And the speed. What was the speed?
Oh, fiber. We're talking. I thought. Oh.
Yeah,
damn it.
fiber. Not first telephone at all.
Oh. Whoops! I gotta do mine over again.
So what was how many megabits? I'll give a hint. How many meg did it transmit at? It's amazing what we've had and what we are at. And it's not that long ago to see that the technology my big thing, I love technology and space, and if you show somebody born 200 years ago an iPhone or any smartphone, they lose their mind what it can do. Do you realize that that smartphone is stronger than, or more powerful than like ENIAC, like some of the first computers that we ever. Okay, what do you got, Bob? So Ray's got
New York State.
Corning.
1970.
Oh, Corning, New York. I got you. 1977, 10 meg. Okay, what's Bob got?
I have Rochester, 1976, 10 meg.
Ray gets 1 point. Okay, you ready?
Oh, what was it? Oh.
Long Beach, California.
Oh.
So it was California, Long Beach,
Really?
1977, 6 megabits.
Wow.
Yeah. Ray got lucky on the one. That was a tough question.
Yeah.
All right, you ready? Oh, I can't do this one because we talked about it. What is Farrell tolerance? I'll take that one out. All right. The name given to modes when they spread in multimode. So what's this problem called? So when we send, specifically when we had LEDs, when the modes spread, what is this condition called? What type of it? Because there's many types of that, Ray.
Modal.
Yeah.
Modal dispersion?
Yeah.
Yeah, that's what I put.
So you're correct. Now, bonus on that one. What have we done? 2, 3, 4, 5. What have we done? What did they do to multimode fiber to combat the effects of modal dispersion?
Took out the center dip.
Right? How'd they do that? What type of fiber is multimode and what type of fiber is single mode?
Right.
This is an ancient one because we don't really worry about this anymore. But so what was the problem is when multimode would send all these modes, because they're not traveling the same path, they would spread.
Right.
Right? And that's limiting factor to distance, and they would mix.
Oh, dispersion shifted? No, that's single mode though.
No. You're thinking right along
Step
lines.
index and
So what single mode is step or, okay, and multimode would be what index?
graph something?
Oh, it starts with a G.
Gradient.
I'll give it to Bob. Graded.
Graded.
So we would
index.
grade the
Yeah.
index of refraction, so the ones on the outside, because they were traveling longer distance would go slower, and the modes on the middle would go faster because we're grading the index of refraction.
well,
Oh,
I can draw what was going on.
yeah, that's what they call it, the peak.
Right. So looking at the index characteristic.
This is the center, right? Yes.
And any light that hit into there stayed there and traveled faster than anything that was coming out the backside, so your signal would disperse.
Huh? See, he's old like me. We don't worry about graded index so much because it was a problem that we can't do anything about except for what we did. So a lot of people have never heard of it. Okay. What is the G stand for in 5G?
Generation.
All right. Because a lot of people, and I saw this online, think it means gigabit. It doesn't. It means generation. And I saw an article on 6G actually. I was looking for something else and I saw they're talking about 6G. I'm like,
And you have people rioting in the streets.
dying from Yeah, I saw.
Remember the peoples in England? They were
I remember
tearing down 5G towers.
well, here's the thing. When COVID was hitting, I don't remember, there's a couple celebrities, Woody Harrelson, John Cusack. So they said that they believed the fact that 5G would spread COVID. I don't know how you put a virus, encode it onto signal. And I remember in England, what you missed was they tore down cell towers. They were 4G. They burnt them.
Oh my God.
And they were 4. They didn't even knock down the right thing. And there's a video online I saw. A guy was installing fiber in England, and a woman came up and says, "Do you have a family?" "Yeah." "So you don't care about your children?" "What do you mean?" "Well, what are you doing here?" "We're installing fiber optics." "As soon as you light these fiber optics up, all the children in this area are going to get cancer." And the guy's like, "Lady, just..." He was stunned. I'm like, it's 2-3 feet underground, encapsulated in a jacket, with a core holding it was amazing to watch some of this stuff. All right. This is advantageous to Ray. The measurement of light gathering ability of a fiber is called its
You gotta write it down. We gotta write it down.
Yeah.
We can't shout out answers.
Yeah, he likes to just shout them out because he's so smart.
Say the question again.
The measurement of the light gathering ability of a fiber is called it's on the spec sheet. So what is the gathering ability called? I'll give you another hint. They call it the cone of acceptance.
That's what I'm going to write down.
So the light has a cone, or I'm sorry, the fiber has a cone, but it doesn't necessarily have a cone. It's not really there, but if light enters outside, it's not going to transmit. If it enters inside the light, and so a camera has this too. And it's bigger on multi-mode than single mode.
Right.
It's a tough one.
Yeah, I don't know.
Angle of...
Angle of incident, angle of reflection, nope. Numerical aperture.
Oh, yeah.
Yeah, the aperture of a camera,
That's
right?
right.
So I'll constantly, I had one that was really interesting. It was they were doing space stuff, and they need to gather light from stars. And they wanted a fiber with a really large numerical aperture because that light, you can't amplify it. It just is what it is. And they're using multiple bundles of it. It was really interesting. And the funny thing is, so we talked to them, and they were, okay, so originally they wanted a polish machine. So why use a polish machine? To cut down on reflections, right? They needed the flattest polish possible. So I'm like, you don't want a polish machine because that's exactly what you don't want to happen is making it low. They wanted a really flat connector. So I said stainless, right? They should use stainless with maybe a hand polish, which seems archaic. But I mentioned the fact that they could send them in and we could do them. And yeah, they're gathering. Oh man, Ray, I did this one.
they're doing like
Spectropathy, yeah.
Right. Yeah, I've seen that where they'll first photograph a section of the sky,
Yeah.
take that photograph and all the pinpoints of the light, they'll expose it onto a metal plate, transfer it to the plate, and then laser those holes. They fill each hole with one fiber optic element.
Really?
They load this back into the telescope.
And they align it exactly the way. They haven't
Right.
moved the scope. It's got to be right in the same spot, right?
Right. Looking at the same stars, and now they can get light measurements off of whatever the 100 or so stars, all at
Really?
individual measurements, right?
Well, that's amazing. I didn't hear. Here's another one. I like going tit for tat here.
Yeah.
I think it was the University of Houston called. They have like this. They told me they had like the second largest telescope in the United States. I said, well, and I helped him with what he was doing, and they're using quantum computers. It's amazing. I worked with another company about quantum. That'll blow your mind with qubits. And I know you were a techie guy. I know you're a geek like me. I know you're like Star Wars like me. Bob, not so much as us, but I said, well, all right, now that I helped you, what are you doing? Oh, we're going to prove existence of life on other planets. I go, yeah, right. No. And I said, what? It's not like you can focus so much, like you can see a person waving at you.
Yeah.
He goes, no, we're using spectropathy with quantum computing, and when they're going to measure what's coming off, and if they detect anything that's considered like pollutants, a non-natural occurring element, that's probably showing the existence of life on that planet.
Some sort of byproduct.
Right.
My brain just,
Yeah.
it was, this is the cool stuff that we work with sometimes, right?
Well, fiber touches every part of the world, you know.
All right. No one got that one. Ready?
Mhm.
What color of light, so we know Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. What of those colors has the most energy? So they're not equal in energy.
Me.
I was going to say red, but it's probably violet.
It is violet. Violet is 1.5 times more powerful than red.
Yeah, the shorter
So-
wavelengths have more energy.
I would like to say that I knew that, but I didn't. Yeah, I didn't know that. I would assume that all the colors were equal in intensity.
Yeah.
They're not. All right. This was another advantage to Ray because he's a geek like myself. Easy question for if you're just gonna know it or not. How many elements in the periodic table? These are cool questions.
Yeah, that changes over time.
It is currently because they have man-made elements now,
Right.
like and the ones that exist for like a half a second and they don't right.
Yeah.
When I was in school, it was like only 109.
Okay, it's not 109. I'll give you that.
When I was in school, I think it was like 120.
Okay, what's our final? I will give a point to the closest, and I won't use Price is Right rules. You can be over.
Let's say 126.
126. What do you say, Bob? What say you?
Without going over?
No, you can go over. It's whoever's closest. I don't know where this Price is Right thing came up, where like you're off by 2, the other guy's off by 10, but you went over. That's
I'm going to say
baloney.
129.
Oh, Bob. 118. Damn it. There's 100. You had said 120. I go, he's got this one. Point Ray. This is almost like the NBA Finals. Celtics are just chomping.
Yeah.
How many? All right, this was cool. How many phases of the moon are there? Full moon, half moon.
4, right?
I don't know. Is that your answer?
Yeah.
Final answer?
Yeah.
I got my producer Jeff over here holding my fingers up.
No, wait, hold on.
Hold on, we're holding.
Yeah,
Write it down. I don't want you guys to.
Yeah.
Write it down. How many phases of the moon are there? See, this is stuff I'm educating right now. You're not going to forget any of these things. Don't look at my paper.
I can't read your writing.
You look. No, that's true. I can't either.
Yeah.
say
8. What do you say?
4.
8. Damn it. I think it's like what? Like 8th quarter.
Oh, I thought it was
half.
like new moon, first quarter, third quarter.
Well, maybe that's it. I don't
full
look,
moon.
Bob. I collect data. I don't. All right. What is the fastest? Okay, a couple points you get here. What is the fastest speed in the universe, and what is that speed? In our known universe, because of course, I'm crazy. I watch these things. Well, if there's multiple universes, the laws of physics may not apply. And these other, I'm like, God, why are you messing with my brain?
Okay.
Okay, Bob.
Fastest speed in the universe
Is what?
is light,
Yes.
and the speed
Photons.
is 300,000 kilometers per second.
Yep. Ray says light, 186,000 miles a second. You're both right. Both get 2 points. Now, do you want to know I've always said 300,000, right? Do you know what it really is? Because, this is important. 299,792, wait, 299,000, no.
Yeah.
Yeah, 299,792,458 meters per second. Which, okay, another bonus. How long does it take the light to get from the sun to the earth? If it's at the surface of the sun, because it could take 1,000,000 years if it's towards the center.
I got it.
to the closest minute.
Closest minute.
I think it's 7.
8. Ray gets it.
Damn it.
This is fun. All right. What is the speed of light in water? Give me it in kilometers. It's right on our manual.
I think I'm torn between 225 and 200. Either way, I'm going to go with 225 kilometers per second.
Okay.
I give up.
225,000 kilometers a second.
I got it.
Bob for the score, yeah.
Wow, I'm coming back.
Light travels, I've always known like light travels 200,000 through glass, right? Which is 120,000 miles a second. I did the math. If you go 1/64th of a second, light travels almost 2,000 miles. And like 1/64. I saw a thing yesterday where it said in a millisecond, light travels like 500 miles or something. I can't remember the number, but it's ungodly.
I read today
Yeah.
that, how they say, when the faster you move, time goes slower for you.
Yeah, well, yeah.
So when you're on an airplane,
Yeah.
if you were to fly from, say, New York to London,
Yeah.
you would have aged 1/10 of a millionth of a second soon, or, slower.
So if you stay on an airplane and constantly go to England, you'll live a lot longer.
You'll
Yeah.
live
Well,
half a second longer.
Yeah, after 100 flights.
Yeah.
So I think the speed of light, at the speed of light travels, I believe, just over 12 inches in a billionth of a second.
12 inches in a bit. Isn't that amazing? So the things, and I know we're talking fiber, and okay, where did that come from? Where did that energy come from?
the sun, I don't know.
Well, originally.
Oh, yeah.
As humans, we know, well, okay, so we bought a piece of lumber at Lowe's. Okay, where did the lumber come from? Came from a tree. Where did the tree come from? An acorn. Where did the first acorn come from? So, okay, we know light. Where did it come from? Where does that pop? And then
I
the
think
theory is what, the Big Bang, where it's the size of a pinhead? Okay,
Where'd that come from?
how do humans know? We always know this came from this. What was before that? And really, time is really just light, right? Because what's going to happen, I watched this video on YouTube, it's like when creation or when time is done. And if you look, it's like 10 billion million years, all the photons will just stop.
Right.
So how do you measure time then? Right? If nothing's happening.
Right. Time ends.
Yeah, it was just in these things that we talk about that we take for granted every day. You talk about an OTDR, right, which we'll do another podcast on those. It's measuring the speed of light in glass at 120,000 miles a second. What's 100 feet?
Yeah.
Like, you take for granted this technology that is superhuman.
Yeah.
I feel like you're holding a nuclear reactor when you have an OTDR, and then you complain that you've spent $3,000 on it, right?
Yeah.
Like, you're measuring photons traveling 120,000 miles a second.
Yeah.
Ray, I can't thank you enough. I don't know how it'll go over, but I like geeking out with stupid stuff.
I got
like
one
this.
question left.
Oh, I forgot. Bob has a really good question for you, Ray.
Okay, if you're stuck in a foxhole,
Stuck in a
the bullets are whizzing by,
Yep.
who do you want in that foxhole to help you get out?
Now, does it have to be real, or can it be make-believe? Could he say, like, Thor? Or does it have to
It has to be a real person.
Okay.
Dead or alive.
Dead or alive, real person.
Chuck Norris, right? Chuck Norris is the only man that can shoot a gun and catch the bullet. He's like 83, by the way.
Jesus.
Who's in your foxhole? Probably John Bruno.
Good question. I was going to say Iron Man until you said it.
Yeah, I see. That's why I knew.
Yeah.
Because you and I we'd be picking superheroes, of course.
Or Magneto.
Yeah, right. Or Thanos with the glove.
Anyways, real person, foxhole.
John Rambo. It's a tough question, isn't it?
Yeah.
Patton.
Yeah, I was thinking. Yeah, Patton, your MacArthur's.
Yeah, right. Your military geniuses. So you told me you were going to ask him that. I had one other question. If you're sitting at a table and you have 3 other spots, and you can pick any human that you, dead or alive, who would sit at Ray Wertz's table? Because this is going to be interesting.
Like a dinner table?
Yeah,
Dinner with
right.
Yeah.
You could have in 1 hour a person's dead or alive. Yeah, another good one. Because I'd have 1,000. I don't know if I could.
I don't know who mine would be.
Who would yours be?
It'd be John
John
Lennon, Paul
Lennon.
McCartney, George Harrison, or Ringo, you know. He doesn't get the cut.
Maybe we could like substitute out George Harrison for Ringo like halfway through.
Yeah, yeah.
Would that would be your first substitute, right?
Actually,
Ringo.
it'd be Paul McCartney, John Lennon, and Mickey Mantle.
The mixter.
Oh, yeah.
All right, yeah, Yankee guy. Okay, Ray, who we got? Final thoughts before we lock you out of your building.
Let's see. I don't know. I'd choose probably maybe a Julius Caesar.
Ooh. See, he's a deep thinker.
MLK.
Okay, Martin Luther King. Yeah, not a bad choice. See, you had it right away. He's drawing deep.
Well, there's just so many different choices. Musically, probably a Geddy Lee.
Okay, so that finishes it up. You know,
Yeah.
who would know that Ray Wertz's favorite band? Say it.
Rush.
And how many times have you seen them?
8 or 9.
I became a Rush fan a little bit later than I should have. I didn't appreciate what that was. Ray and I went to a Kiss
The
concert.
credits music cons.
And I want to thank Ray for being here, and also my sidekick Bob, who's
Thank you, Ray.
always amazing.
Thank you. Fun.
Ray, go home.
All right.
Thanks, guys.
guys.
All right. See ya.